Hello and welcome. My name is Ralf Gerlich and I would like to present to you the results of our study on the effectiveness and efficiency of automated software verification tools. But first I would like to tell you a little story. Once upon a time there was a software manager with a development team. And the team had to produce software for space application, and that software obviously had to be reliable. So the team would regularly produce new releases of the software, review and test them, and record the results from the reviews and tests, and possibly fix the defects that needed fixing. That was a lot of work, and so the manager thought maybe we can improve the situation by using one of those automated software verification tools. That tool would find all the runtime defects on its own, and we would have less work. So said and done, they selected a tool and applied it to their software. Bummer. The tool produced a lot of reports, and many of them were even wrong in the sense that they highlighted defects that weren't even there. So they had saved some work, but they had created new work. And so the manager wondered, maybe they could have selected a tool better suited, or they could do something different in their development that would make life easier for the tool and for them without, in essence, adding overall effort to the project. And for that, the manager would have to review many tools. There's so many tools on the market, and the ones that we have on the slide here are just a small selection. Also, there's many different methods that these tools use, and they have a very different impact on the effectiveness and efficiency of the tools. And finally, we would need some terms to actually define what effectiveness and efficiency is and how to distinguish the tools further. So let's start with some of those terms. The first set of terms is about the correctness of what the tools report. We would talk about positives and negatives, and true and false positives and negatives. And it's quite easy to remember. A positive means the tool reports a defect, and vice versa. A negative would mean that the tool does not report a defect, or even more specifically, the tool might explicitly report absence of a defect. And false means the tool is wrong, true means the tool is right. So a true positive is a report about a defect that is actually in our software. And a true negative would mean that the tool does not report defects that are not there. We would of course want to have only those true cases. However, we might have to deal with false positives and false negatives, and we don't want those. We don't want false negatives because it means that there is a defect present in our software, possibly a critical defect, that the tool won't highlight, and so we won't be able to fix it. On the other hand side, a false positive means that the tool reports a defect that isn't there. But to find that out, we first have to spend some effort analyzing the report and then to conclude that the defect is not present at all. So we just spend time without having the reward of being able to fix a defect and thereby improving the quality of our software. So obviously our best selection would be a tool that doesn't have false positives or false negatives. Unfortunately, one basic result of theoretical computer science is in the way of that, and that is Rice's theorem. Rice's theorem can be expressed as non-trivial properties of programs are non-decidable, or as it means for us, no tool can avoid both false positives and false negatives. There can be tools that have no false positives, but they will have false negatives, and there can be tools that have no false negatives, but they will have false positives. And there can be tools that have both. So when we are selecting our tool, that means that we actually have to characterize it by the amount of false negatives and false positives we get relative to the defects that are of interest to us. And how do we characterize the tools in that manner? Well, we compare them by a systematic approach. We take a piece of software, as we did in this study with the flight application software of an Earth observation satellite with proper size and representativity for our endeavor. And we take that software and put it into the tools and record what the tools give us back as reports. So from each tool we get a list of reports saying that the tool has detected defects at specific locations. We then take these lists of reports and funnel them through to get a consolidated report. And there we would have only one single line per defect reported by at least one tool. And if multiple tools reported it, it would still stay a single line. So let's have a little look at such a consolidated report list. We would have here some basic information about where the defect should be located. And we would then have information about the type and about the tools that reported it. So in this case, tools 1, 2, and 5 reported it, and tool 3 and 4 did not. Now we would select some of these reports. As I said, there will be many of them, so we can't sample them all, but we would sample some of these reports and look into them more in detail to find out whether they are actually true positives or false positives. Let's say we come to the conclusion that this area index out of bounds defect is actually a true positive. So we could count it as a true positive for the tools that have reported it, but as a false negative for those that didn't. Vice versa, the unreachable code may be a false positive here, so it would count as a false positive for those tools that reported it, but as a true negative for those that didn't. And with that, we can establish some statistics about the tools that we can compare. Unfortunately, we were not able to get enough reports analyzed in this exercise. It took between 4 minutes and 4 hours to analyze a single report and to consider all the relevant parts of the software that may be in play here. So we didn't derive statistical figures this time. However, we still can see some qualitative features of the tools from the exercise. The tools in our study, we had 5 tools here, and unfortunately I cannot name them due to license restrictions with the vendors. Still, the study may be able to give you some basic insight into what to look into when selecting a tool. The first 2 tools are abstract interpretation tools, and they have a property that is called soundness, which I will explain in a minute. Another tool also using abstract interpretation, but without this property of being sound. It's simply keeping back some reports in order to reduce the amount of false positives that may occur. Our tool number 5 is a symbolic execution tool, and that essentially is testing, but with symbolic values instead of concrete values. And finally, we have an actual testing tool, which is our own tool, DCRTT, which is using random testing or fuzzing to look into the code. So we have one dynamic analysis tool in here, which is DCRTT, and 4 static analysis tools. And I promised you that I would define the term of soundness. And for that, we have to look into 3 different situations. There's the situation where an operation that is to be checked is safe in any case. So looking at this example here, we have this variable called a, which is assigned the value pi over 2, and we shall assume that it's not changed anymore somewhere else in the code. So when we reach this statement here, sign a will evaluate to something close to 1, so this division is safe. And a sound tool might see that and then certify that sign a will never be 0, and soundness would mean that we can trust this statement. On the other hand side, there are faults that are always occurring. For example, here when we assign pi to the variable and also not change it again before we get to this statement here, then sign a would be 0, and this would be a division by 0. And if a sound tool tells us that sign A will always be 0 in all cases that we get to this statement, then due to the soundness, we should be able to trust this tool. Finally, we have the two extremes. It's always occurring or never occurring. And in between is the case where it's not always occurring, or it's occurring sometimes, or it might not be possible to decide whether it's occurring at all. So to represent that, we have the case here where we have an external parameter time that cannot be constrained any further. So A may take any value, including multiples of pi. And that would mean that we have zeros here. In that case, a sound tool, the only thing a sound tool can do is to say, I cannot decide whether sign A may or will be 0. And so we will have to check on our own. This might as well be a false positive, and or it could be that there are actually cases where the division by 0 may happen. Another distinguishing feature of tools may be whether they consider context. So if we look at a single expression or statement, the context is all the code that has been executed leading to the execution of the statement or expression that we are looking at. So it may be very well the whole call tree or just the code that is in the same function as our statement. So a tool considering context might see this instruction here and might see that A isn't changed anymore before we get to this expression. And so it might consider the information that it has from context when deciding whether that expression is problematic. And in our case, the tool might say, that's all right, sign A is never 0, so there's no division by 0 here. I know that because I have considered this context. On the other hand side, we might have tools that are not considering context. So for such tools, this assignment here might be invisible. So they would get to that statement and they wouldn't know anything about the value of A, and they would have to conclude that it might be a multiple of pi, leading to sign A being 0. So such a tool would have to tell us, I don't know A, so sign A might be 0. And we would of course conclude, looking at the context here, that it is a false positive. So of course we would prefer using tools that consider all the context, because it seems like they wouldn't produce as many false positives. However, considering the context may be a costly operation, and tools may be limited in considering context. They are limited by the available CPU time and the available memory. So representing that context may take up a lot of memory, and processing it may take up a lot of time, but we don't want to wait indefinitely for our results, and we don't want to have to run this all on some supercomputer with terabytes or petabytes of RAM. So tools may become overwhelmed by context, and we can look at that in this example. Here we have a statement, an assignment that assigns pi over 2 to the variable a. And here we have our call tree, and a might be passed down to the function containing this expression, where a is used as a parameter to the sign here, and then the result is used as a parameter to the division. And now in order to find out that this division cannot lead to a division by 0, we would have to know this context, of course. So a tool that is processing this code might start at the top and see, okay, there's the statement a equals pi over 2, and say, I know a now. Now, the same tool might then go through the whole code and through that whole call tree and collect additional context information. And at some point it might conclude, there's so much information now, I cannot store anything more, I need to drop something. Or it might conclude, the context has become so complicated that I'm using up too much CPU time to process it. So I will drop some of the information. And it might drop the information that I is pi over 2. So now it can't remember a. And finally, it gets to this expression here, and because it doesn't know the value of a, it cannot conclude that this operation is safe, and it will report to us that that might be a division by 0. And of course, we, looking at the context, would conclude that that, again, is a false positive. There are also other limitations to representing context. We cannot represent context exactly, because if we are representing it exactly, we try to do something that Rice's theorem tells us is not possible at all. Also, we want to be efficient with the memory and time that we have. So many tools use an interval approximation to represent the values that expressions or variables can take. And we will illustrate this on this example here. We have a function here that accepts an unsigned integer as parameter, passes that on to the map to set function and uses the return function from that as an index unless it is 255. And looking at map to set, we see that map to set checks the value of the input parameter, and if it's 0, 1 or 2, it simply returns the value unchanged. Otherwise, it will return 255. So we know that at this point, index can only be 0, 1, 2, or 255. And by the if statement, we exclude the latter. So at this point, index can only be 0, 1, or 2. And all of these three values are valid indices into that array. So we know that this piece of code at least does not have an index out of range problem. Now our tool might be looking at the map to set function and conclude that the result of map to set is in the range from 0 to 255. It's representing that in this interval representation. And the tool is not wrong. All the values returned by map to set are in that range. However, in that range, there are also a lot of variables or values that map to set will never return. And following that, the tool would then conclude that after this if condition here, the index might be in the range from 0 to 254. It concedes that 255 is not possible anymore. But there's lots of values here that are invalid indices for my array. And so the tool would warn us, hey, the index might be out of range. And of course, us looking at that, we would say that's a false positive. And that is due to the specific representation of the context here using intervals. And one of the most known tools of the sound static analysis tool domain is polyspace code prover. Polyspace code prover uses a representation of the values of multiple variables that is a polyhedron. But in essence, the individual ranges of individual variables are again projected onto intervals. So there's many tools that use this interval representation or a similar representation. The other problem that a tool might have is dealing with arrays. Arrays might be complex, might be long, and it might be difficult to represent knowledge about each individual entry of the array. We will illustrate this with this example. Here we have some main function, myfunc2, and it calls myfunc with a parameter of 2. And myfunc then uses that as an index into a map to determine the number of bytes that shall be copied from source to destination. And if we look at index 2, we see that it specifies 5 bytes to be copied, and that is valid both for source and destination. So we know that in context, this example does not have any out of memory issues or out of bounds issues. Now the tool would look at that and say, well, the range of map of index is 1 to 78. It doesn't look or might not look at the index in detail, or it might just constrain the index a little bit and then concede on or decide on the range of the values in that index range. Now we know that there are several values in that range that wouldn't be valid as a length for this copy operation. And the tool, of course, also knows that and warns us about it. It would say there is a possible invalid index for the destination because, for example, 7 is in that range and it's an invalid length that we have here. However, we would say, well, looking at map of 2, we see it's 5, so there's nothing that can happen here. This is also a false positive. And the result of all those inaccuracies together is that we might get a lot of reports. So we tried different configurations for each of the tools, and that explains the large range that we have here. But if you look at the graph here, you see that you may be in the thousands or tens of thousands of messages that you get. And of course, our manager now asks, how shall my team handle thousands of messages? We need to look through all of them. Well, if you don't have almost unlimited resources, it's difficult or even impossible to deal with that amount of reports if you are greeted by it. What you might do is now prioritize analysis of messages. So that means you're not analyzing all the messages anymore. And that means even if you're using a sound tool, which would have no false negatives, you could now get false negatives because you're ignoring some reports that might be true positives, and by ignoring them, you do as if the tool didn't report them. So while the tool itself may be sound, your method or application might be unsound. Fortunately for our manager, there are some countermeasures available, and we list some of them in our paper. I just want to focus on one possible countermeasure here, and that is we could reduce the context domain. If we have this kind of large call tree, we might split the functions into different modules like this and analyze the modules individually. That also would mean that the call context that we have here from module 1 calling module 2 would vanish. So we would have to reintroduce that. We would have to make each of these modules self-contained in the sense that they are robust. You could add checking code at the beginning of each of the entry functions, checking whether the input values are valid. And that would give your tool that you're using a clue that these values that are filtered out there cannot proceed further into the code to avoid false positives from such inputs. And essentially that way you would be defining the required context here. What is difficult to represent with static tools is dependencies in complex or dynamic data structures. One example for such a data structure could be a telecommand, where you have a header containing the command information and a payload containing data for the command. And of course, the structure of the payload depends on what command is specified in the header. Another example would be configuration data or your data pool. And static tools have problems with that because it's an insane amount of information that has to be specified here, and that may be too much information for a static tool to handle. It's essentially context information, and that may be dropped. For a test tool, that's not even special. You can just generate test inputs according to the specification for the telecommand structure and thereby avoid injecting invalid telecommands. You could inject invalid telecommands if you want to do robustness testing, but there you can easily balance the amount of invalid commands and valid commands that you inject. So finally, I would like to make a little comparison between testing or dynamic analysis and static analysis. We've seen that static analysis can analyze all cases in which software or a piece of software can be used simply by looking at the whole input domain. For testing, we sample inputs from the input domain, and we normally cannot say anything about the cases that we didn't test, except if we have some equivalence cases available. For static analysis, using sound tools, it is possible to avoid false negatives, but only if you analyze all the reports that are available. Testing can have false negatives due to the sampling approach. However, in order for static analysis to avoid false positives, it needs to consider context, and in doing so, it is limited by the available CPU load and memory, while testing simply executes the code and thereby implicitly considers all the context that is there. So as a consequence, static analysis may lead to a possibly high number of false positives, while testing can avoid false positives completely if you have a representative test environment. But you can scale that in a sense by using more and more representative test environments until you test on your target. So that completes my presentation. There's more details in the paper, among them, for example, how we simulated multitasking and more details about our evaluation method. I would like to leave it at that with my presentation and just ask you, what is your experience with automated software verification tools? Thank you.